This accompanying video presents results of our amortized supersampling framework under scene motion. Traditional real-time rasterization of procedural shaders can lead to excessive aliasing if the underlying signal is not band limited. The artifacts are evident in the checkered marble procedural shader, particularly near the horizon. Using reprojection to pull additional information from pixels generated in earlier frames causes excessive blurring due to repeated interpolations as evidenced here. It also causes aliasing due to lack of data at recently disoccluded regions as shown here. Our method, which uses subpixel buffers and an adaptive recursive filter, avoids this problem and thereby yields significantly better results as shown here. The resulting rendering is qualitatively similar to a pre-recorded 4x4 stratified supersampling result, which has a bit less noise but more aliasing near the horizon. Note, however, that 4x4 supersampling is 6 times slower than our approach. Now we demonstrate improved handling of reprojection cache misses due to disocclusion. Here we color code the number of subpixel buffer cache misses occurring in each pixel. Darker shades of red indicate a larger number of cache misses. Note that all cache misses are concentrated on a small number of pixels of the screen. If we do not perform additional shader evaluations to compensate for the lack of information on disoccluded regions, aliasing artifacts are clearly visible. However, by performing additional shader evaluation for each of the small number of cache misses reported in the scene, quality improves significantly. This is clearly evident in the highlighted regions. We also present a model to measure the amount of blur introduced by repeated reprojection under scene motion. Given a user-specified error tolerance, the recursive filter is dynamically adapted, allowing the user to trade off aliasing due to limited data reuse and blurring due to excessive data interpolation. Note that by selecting an appropriate tolerance, our results approach that of the reference ground truth image. The paper also presents a model to detect changes in the shaded signal, such as the shifting illumination in this teapot scene. This technique also adapts the recursive filter. Here, a user-specified error tolerance trades off supersampling quality for responsiveness to changes in signal. Using a larger tolerance causes the shading to be outdated, as shown here. Again, note that by selecting an appropriate tolerance, our results better approximate the reference ground truth image. Finally, we show comparative renderings under motion for the scenes from the results section of the paper. Note that our results are comparable in quality to 4x4 supersampling, but at a fraction of the rendering cost. All videos were recorded in real time except for 4x4 supersampling and the reference ground truth image. All experiments were performed on the GPU of an Intel Core Duo 2.13 GHz PC with 2 GB of RAM and an AMD HD 4870 graphics board. Thank you for your attention.